more of a problem in coding theory, because in cryptography it's different. In cryptography, usually you start with an access structure and then you construct the best possible secret sharing scheme for that access structure. So that's what we did actually in the first part of the talk. So for this one, it's more of a coding theoretic problem. So now the next one is I will describe an application of secret sharing, in particular in secure multi-party computation. And then I will go back again to the minimal code words problem. Okay, so first we define multiplicative secret sharing scheme. Okay, so suppose we have a linear secret sharing scheme and it's represented by a monotone span program. So I hope you still remember monotone span program. It's a very long definition, but it says is if you have two secrets, S and S prime, so basically for these two secrets you have the corresponding shares. So for S, suppose the shares are x1 to xn. For S prime, suppose the shares are this one, x1 prime to xn prime. Now, we are interested with the product of the secret, the two secrets. So we have two secrets. We consider their product. The question is, what happens to the shares, the corresponding shares? So we say that a scheme is multiplicative if it satisfies this property. So this means that the product of the secrets is a linear combination of the product of the corresponding shares. This one is inner product. So that's what we mean by multiplicative. So the product of the secrets can be computed as a linear combination of the product of the corresponding shares. Now, we say that scheme is strongly multiplicative if you take any subset not in the access structure. So if you consider the restriction of the scheme to the complement of A, so if you remove the participants in A, the resulting scheme is still multiplicative. So you still have this property. But your shares now are just limited to the shares of the complement of A. So that's what we mean by a multiplicative scheme. Now, to characterize multiplicative schemes, it depends on the access structure. So it's not, you cannot construct multiplicative schemes for all access structure. So the access structure must satisfy this property. So it's called QD. So an access structure is QD if you take any D sets in the not in the access structure. So their union, it doesn't cover the set of participants. So that's what we mean by QD. So if D is equal to 2, if you take any two sets that are not in the access structure, so say A1 and A2, if you take the union of A1 and A2, it's a proper subset of the set of participants. So that's what we mean by Q2. Then you also have Q3, so 3 subsets. Usually that's what we use for multiplicative schemes, Q2 and Q3. An example is the T out of N threshold structure. So when we say T out of N, again, any subset of size at least T is in the access structure. So this is Q2 if N is greater than or equal to 2T minus 1. And then it is Q3 if N is greater than or equal to 3T minus 2. Maybe I'll explain this one, Q2, because if you take two subsets not in the access structure, so the maximum size is 2t minus 1. If you take two of them, you have 2t minus 2. Now, to satisfy this, we must have n is greater than 2t minus 2. So n is at least 2t minus 1. So any two sets not in the access structure, they cannot cover the whole set of participants. And then there's this result by these three authors. So given any access structure, gamma, then there exists a multiplicative linear secret sharing scheme over FQ realizing gamma if and only if gamma is Q2. So you can always construct multiplicative scheme as long as the access structure is Q2. So again, you will see an example will be the Shamir threshold scheme. So this is how special this secret sharing scheme is. So we consider two secrets, S and S prime, and then you suppose these are the corresponding share vectors, applying the Shamir threshold scheme. Now, if you remember, these shares are evaluations of polynomials. So there are points in the polynomial. Now, if you look at the product of these two secrets, S and S prime, so you look at the product of the two polynomials, f of x and g of x. So the degree of this product, so since f and g have degree at most t minus 1, so the degree of the product is at most 2t minus 2. So if you have at least 2t minus 1 points, you can reconstruct the product of the two polynomials. So that's why we have this. If n is greater than or equal to 2t minus 1, then the Shamir scheme is multiplicative. And then if n is greater than or equal to 3t minus 2, it is strongly multiplicative. So it is an example of a multiplicative scheme. But take note, by the time when Shamir proposed this scheme, you don't have the concept of multiplicative, strongly multiplicative. But it turns out this scheme, it satisfies this property. So another example of a multiplicative dual code. Now, if you take two code words of C, so the dot product is 0. So that's why you have this. And if you apply the mass scheme, the first coordinates are the secrets, C sub 0 and C sub 0 prime. So since the dot product is 0, it implies the following. So the product of the secrets is a linear combination of the product of the shares. So it is multiplicative. So the schemes based on self-dual codes are multiplicative. Now, it is an open problem to find more examples of multiplicative and strongly multiplicative secret sharing scheme. In particular, strongly multiplicative, this one is a more difficult problem. The only examples of strongly multiplicative schemes are the Shamir scheme, and the other ones are actually from algebraic geometric codes. So it's an open problem to find more simple examples of strongly multiplicative schemes. Now, this concept of multiplicative, strongly multiplicative schemes, it's used in secure multi-party computation. So it's another cryptographic protocol. So I will give an overview of this one. So what do we mean by MPC? So in a secure MPC, we have the following. So we have n participants who want to compute a function. Now, the requirement is the following. So when they so each participant, they have the input. Each of them has an input to the function. So the first requirement is the output must be correct. The second requirement is the privacy requirement. So the input of each participant must remain private. So the other participants, they cannot know the inputs of the other participants. So that's what we mean by secure multi-party computation. Now, it's easy to implement this if you have a trusted third party. So if you have a trusted third party, you just simply give the inputs to the third party, so the third party will compute the function. But the problem is, you don't have a trusted third party. So how do you perform computation of a function without a trusted third party? So you only have the participants to do that. So one way is to use linear secret sharing schemes. So I will describe how to apply the linear secret sharing schemes to perform secure multi-party computation. So first, we assume the following. This is a general assumption in MPC. So when you implement an MPC, it's represented by a circuit over a finite field where the gates are addition and multiplication. Well, this means that if you want to construct an MPC protocol, it is sufficient to construct protocols for addition and multiplication. It's because you can express any function as a combination of addition and multiplication gates. So you just focus on secure addition and secure multiplication. So for secure addition, it's straightforward for secure addition. So suppose you have a linear secret sharing scheme that is multiplicative. Actually, we don't need the multiplicative for addition because we only need the linearity of the scheme. So if the scheme is linear, it can provide secure addition. Because if by linearity, suppose A and B here, you can look at this as secrets, A and B. So, and then suppose these are the corresponding shares. So this is the corresponding shares for A, corresponding shares for B. So if you consider the sum of these two secrets, the shares for this secret is just the sum of the shares, because the scheme is linear. So the sum of the secrets, it corresponds to the sum of the shares. So you can perform secure addition. So to perform secure addition, so at the start, each participant share its input using the scheme. And then, so the circuit is processed gate by gate. The intermediate inputs and outputs are also shared using the secret sharing scheme. So each input and output, you share using the secret sharing for it to be secure. Now, for multiplication, this is where we use the multiplicative property. So recall, if the scheme is multiplicative, it satisfies this property. So the product of two secrets is a linear combination of the product of the shares. So it's not same as in addition, wherein the sum of two secrets is just the sum of the shares. So for the product, you don't have the property that the product of two secrets is just the product of the shares. You don't have that in general. So what you have is this for multiplicative. So to perform secure multiplication, this is the first step. Each participant P sub I computes this quantity. So P sub I, so participant P sub I has A sub I and B sub I, the corresponding shares from A and B. So he can compute this one. And then C sub I prime is shared using the scheme. Okay? So for each C sub I prime, suppose these are the corresponding shares using the scheme. So this is, one of the values here is given to the other participant. And then the next step is participant P sub j using the received values will compute this one, C sub j. So linear combination of the values that the participant receives from the other participants. So here, P sub j computes this linear combination. R sub I is the same the recombination vector. So you can verify that this C sub j's obtained here, this will be the shares for the product of the secrets. So this enables to perform secure multiplication. Okay, so that's how we apply the secret sharing schemes in secure MPC. So now I want to return to the minimal code words, but this one, this is more coding theoretic problem. So let's recall a minimal code word. So a minimal code word is a code word with minimal support. Okay, so it has this property. Now, the main problem here is given a linear code C, so determine the set of minimal code words. So if you remember an application of this one, if you determine the minimal code words, you can determine the access structure of the corresponding secret sharing scheme. So that's one application. The problem here is this is a difficult problem in general. Determine the minimal code words. Okay, so let's go back to matroids. So if you have a linear code C, you take a generator matrix of C. You remember if you have a matrix, you can form a matroid, the vector matroid. So for a linear code, there's a corresponding vector matroid. So based on the linear dependence of columns of generator matrix. Now, the circuits, the maximal dependent sets, minimal dependent sets. The circuits are actually the minimal code words of C. So minimal code words you can view as circuits of a matroid. Another interpretation is in terms of graphs. So suppose you have an undirected connected graph G with vertex set V and edge set E. And then we define the incidence matrix of the graph. So the incidence matrix, it's an M by N matrix. So the rows are indexed by the vertices. And then the columns are indexed by the edges. So it's a vertex by edge matrix. And then the entries are defined as follows. So the ij entry is 1 if the vertex V sub I is in the edge E sub j, and then 0 otherwise. So that's the incidence matrix. Now, we can use the incidence matrix to obtain binary linear codes. So you consider the span of the incidence matrix over F2. So we can obtain 2 binary codes from the incidence matrix. So the row span of the incidence matrix is what we call the bond space. So in graph theory, they study this bond space of the graph. So it is a binary linear code of length n, dimension m minus 1. And then the dual code is what we call the cycle space of the graph. So it has length n, dimension n minus m plus 1. Now, if you remember, the length is n. It corresponds to the edges. So the coordinates corresponds to the edges. So you can look at the code word. You can look at the code words of these two binary codes as a subset of edges or subgraph of the graph G. So you can look at the code words as subgraphs of G. Now, if you interpret the minimal code words of these binary codes, well, the interesting one is the cycle space. If you look at the minimal code words of the cycle space, it corresponds to the cycles in the graph. And then, if you look at the minimal code words of the incidence vectors of the bond space, it corresponds to the capped set of the graph. So this is another way to look at the minimal code words of a linear code. So it can be interpreted as cycles in a graph. Now, some applications of minimal code words. So I already mentioned this, decoding algorithms, and then secret sharing. And a more recent application is secure two-party computation. Now, let's look at some general properties of minimal code words. So, it was given by these researchers. So the properties are as follows. So C is an NKD linear code, H is a parity check matrix, and then we take a non-zero code word. So let us denote the support by U. Okay? So one property is the following. C is a minimal code word if and only if we have the following. So the rank of this matrix is equal to the size of U minus 1. Now, what is this matrix? This is the parity check matrix restricted to the columns corresponding to the support of C. So you have C, you consider the support, you consider the corresponding columns in the parity check matrix, and then you look at the rank of that matrix. So if the rank is equal to this, C is minimal. The second property is if C is minimal, then the weight is bounded above by n minus k plus 1. So it cannot have a big weight. Third property is if the weight is small enough, you can already say that C is minimal. This is, if you look at the binary case, this bound will be 2d minus 1. So twice the minimum distance minus 1. So if the weight of C is less than or equal to 2d minus 1, it is minimal. Next property, the span of the set of minimal code words is the whole code. So each code word can be expressed as a linear combination of minimal code words. And then for binary codes, we have this property. If C is non-minimal, then you can write C as the sum of two code words with disjoint supports. So let's look at the proof of the first property. So sometimes this is called the H test or parity check matrix test. So C is minimal if and only if the rank of this matrix is size of U minus 1. So let's look at one direction of the proof. So we assume that C is minimal. Now, if you take a code word of C, it satisfies this property. So C times the transpose of H is 0. And then this is equivalent to saying that the columns of this matrix are linearly dependent. Because this is a linear combination of the columns of this matrix. Non-trivial linear combination. So these columns are linearly dependent. Now, if the rank of this matrix is less than this one, less than the size of U minus 1, it implies that there exists a proper subset of columns of this matrix that is linearly dependent, because the rank is less than this one. But if you have a proper subset of columns that is linearly dependent, it corresponds to another code word of C. So there exists a non-zero code word C prime of C, such that the support of C prime is a proper subset of the support of C, because it corresponds to a proper subset of columns of this matrix. So it contradicts the minimality of the code word C. The other direction, it uses the same, similar argument. An equivalent formulation of the H test is the G test generator matrix. You can use the generator matrix. So it was also given by Agrell. So if you use the generator matrix, you consider the this matrix. So you consider the complement of the support. So you consider the complement of the support, and then you look at the restriction of the generator matrix to those positions. So if the rank is k minus 1, so 1 less the dimension of the code, then you can say C is minimal. Those two are equivalent. Okay, so we can use the general properties to determine the minimal code words. So I will describe in the case of binary codes. So applying the properties, we have the following. So for each code word of C, so if the weight is less than or equal to 2D minus 1, C is minimal. If the weight is greater than or equal to n minus k plus 2, C is not minimal. Because for minimal code words, the weight is at most n minus k plus 1. The problem is here. If the weight is from 2D to n minus k plus 1, so it is possible that you have minimal code words and non-minimal code words. So for this one, the only available tool is to use the H test or the G test. So actually, it's an open problem if you can improve this process. Because if the number of code words is very large, this algorithm is very inefficient, because you have to check basically each of the code words. You can do some improvements using automorphism group of the code. So for example, if it's a cyclic code, so in a cyclic code, if you take a minimal code word, the cyclic shift is also minimal. So you just consider the equivalence classes. So somehow it improves the complexity. But in general, it's difficult to determine the set of minimal code words. So some examples of codes where we can determine the minimal code words. So let's say the binary Gole code, 2312.7. So if you look at n minus k plus 2, so it's equal to 13, and it's equal to 2D minus 1. So this implies that the minimal code words are the code words of weight at most 12. So it cannot exceed 13. Now, if it is an MDS code, so we already know that the minimum distance is n minus k plus 1. So this is already the maximum possible weight for a minimal code word. So the only minimal code words are the minimum weight code words. And then for Hamming codes, you have this formula for the minimal code words. But in general, this quantity is unknown for linear code. So one problem that you can consider is the following. Instead of looking at the actual value of M of C, so you look at the maximum and minimum size of this set. So we consider the maximum number of minimal code words. So we look at this quantity. So you consider all the binary NK linear codes. And then you define M of NK, so the maximum of M of C such that C is an NK binary linear code. Now, in graph theory, they already studied this one. So if you remember, you can look at the minimal code words as cycles in a graph. So they already studied the number of cycles in a graph. So one result is the following. So a connected graph with m vertices and n edges cannot have 2 raised to n minus m plus 1 or more cycles. But you will see we can actually prove this using coding theory. Now, for matroids, it's also studied. So again, you remember, minimal code words are circuits of a matroid. So for matroids, it's also studied. If you have a matroid on n elements and rank r, it has at most n taken r plus 1 circuits. So we look at the case of binary linear codes. An easy upper bound is the following. So if you have an nk binary code, the number of code words is 2 raised to k. So the number of minimal code words is at most 2 raised to k minus 1. So it's the trivial upper bound. But if you apply to the cycle code, cycle space of the graph, so recall that the cycle space is an n minus m plus 1 linear code. So if you apply this trivial upper bound, you will have this. M of C is at most 2 raised to n minus m plus 1 minus 1, which is this theorem. A connected graph with n vertices and n edges cannot have 2 raised to n minus m plus 1 or more cycles. Now, one question here is, are there binary codes which satisfies equality? So all non-zero code words are minimal. So they are called intersecting binary codes. So a binary code is intersecting if the supports of any two non-zero code words are not disjoint. So they intersect, that's why it's called intersecting. Actually, this was studied because of a different motivation, not because of minimal code words. But it turns out they are related. So a binary linear code is intersecting if and only if the minimal code words are all the non-zero code words. Now, let's look at some bounds on this quantity. So this one is the maximum size of M of C, minimal code words. So for the matroid, so we have this theorem. So a matroid M has at most n taken r plus 1 circuits. So we look at the proof. It's by induction on the number of elements of the matroid. So let B be a basis of M. Now, if M is already equal to the basis, then it means that it has no circuits. So the number of circuits is 0. So we have this. So now let us assume that there is an element of A which is not in the basis. So M is not equal to B. So what happens is M minus A has rank R. because a basis is m minus a. And then by induction, so it has at most n minus 1 taken r plus 1 circuits. N minus 1, this is the size of m minus a. And then r plus 1, this is the size of the circuits. Size of the circuit. So you take n minus 1 taken r plus 1. Now, as all bases have cardinality r, so there are at most n minus 1 taken r bases. So again, n minus 1 is the number of elements of n minus a. So a base has cardinality r, so there are at most n minus 1 taken r bases. Now for each basis, there corresponds one circuit. So every circuit containing A can be constructed from a basis. It's not enough. Okay, so every circuit containing A is a fundamental circuit. So the matroid has at most n minus 1 taken R circuits containing A. So if you sum those two quantities, you get this one. Now, as a corollary, we have the following. So for binary codes, M of nk is at most n taken k minus 1. So you just look at the connection between a linear code and matroid. And then you apply the bound, you will get this. Now, for binary codes, when do we have equality? So when is m of nk equal to n taken k minus 1? So this is satisfied by the binary MDS codes. But the problem is, the only binary MDS codes are the trivial codes. So k equals 1, n minus 1, and n. But for non-binary fields, this is satisfied by the MDS codes. Another upper bound is the following. So this one is again by Agrell. And it depends on the rate of the code. If the rate of the code is greater than 1/2, so we have this upper bound. Another upper bound is the following. So this one is a recursive upper bound. M of nk is so it's at most m of n minus 1 k minus 1 plus n minus 1 taken k minus 1. Okay, so the proof of this, I think it's already okay. I think it's already okay. It's already. Okay, so we look at this upper bound. So to prove this one, we start with, suppose we have a binary code satisfying the maximum. So m of c equals m of nk. And then you take parity check matrix of this code, and then you remove the last column. So you have a parity check matrix, you remove the last column. And then you assume that the rank of H prime is n minus k. So it's still the same rank. So how do we count the number of minimal code words? So let's take a non-zero minimal code word in C, and then you look at the last coordinate, x sub n. So the last coordinate is, the only possible values are 0 and 1. If x sub n is 0, so the last coordinate is 0. So if you project to the first n minus 1 coordinates, it will be a minimal code word of this code, the null space of H prime. So it's an n minus 1, k minus 1 code. So there are at most m of n minus 1, k minus 1 such minimal code words. Now, if x sub n is equal to 1, so again, you consider the projection on the first n minus 1 coordinates. So they form an independent set of the column space of H prime. So you will have this number of possible x prime. You just compute for the number of linearly independent set of columns. So you have n minus 1 columns for H prime, so you take n minus k. So it will imply this bound. Now, for lower bounds, actually for lower bounds, there are only 2 lower bounds. So one of them is the following, by Ashikmin and Barg. So here they use random coding. So they take a random code and then they compute it for the expected value of m of nk. So they will have this lower bound. Another lower bound is the following. This one is straightforward to prove. We just use the following. If you remember the set of minimal code words, the span is equal to the whole code. So every code word is a linear combination of minimal code words. So you just use that to obtain that lower bound. So let's see be an NKD code. So by induction, every non-zero code word can be written as the sum of at most n over d minimal code words with pairwise disjoint supports. So you can have this. You just count those. You count those possible linear combinations. So it will be at least the number of non-zero code words. So that's why you get this lower bound. The problem with this lower bound, it's not a good lower bound. If you compute for the exact values, it doesn't give a good lower bound. So it's still an open problem to obtain better lower bounds for this quantity. So just to summarize, so for this quantity, so the maximum of number of minimal code words for binary codes, we have the following upper bounds, and then we have the following lower bounds. Actually, we also computed for exact values of this, for small values of n and k. So we have some values for this one. So now we can also look at the minimum number of minimal code words. So there are less results on this one as compared to the maximum case. So we similarly define this quantity. So small m of nk is the minimum of the number of minimal code words of binary codes. So some bounds are as follows. So m of nk is at least k. And then if C has distance at least 2, it satisfies this lower bound. And then this is another lower bound. If C has dual distance at least 3, then the number of minimal code words is at least the length of the code. So that's the end of my talk. Thank you very much.
Thank you, Dr. Romar de la Cruz, for the lecture on secret sharing protocols in the second session. Please stay on the stage. There's a souvenir from the committee. May I invite Dr. Al-Suciana to come to the stage and hand over the souvenir to the speaker. Please give an applause to Dr. Romar de la Cruz. This is the end of the second session. We will have an hour for lunch and pray. The participant may get their lunch box over there. The third session will be started at 1:30 p.m. Before that, if you want to take your reimbursement, please come to the registration table. Thank you.